Welcome back to Multivariate Calculus. In this video, we're going to be looking at regions of integration. We're extending the idea we talked about previously of iterated integrals, and we'll look at some examples in this video where the region where we're integrating is not quite so straightforward. We'll look at a couple of examples that are showing you how you can change the order of integration. And at the end of this video, we'll look at an example where changing the order of integration takes the problem from something that is not solvable to something that is. So let me get my head out of the way and let's dive right in with an example. Let's look at f of x and y is equal to x times y. And let's look at a region that's going to be defined graphically. And that's going to be fairly common in this lesson. Instead of giving you the bounds of the region as stated inequalities, I'm going to show you the picture of the region and ask you to figure out what the bounds are going to be. Because sometimes it's going to be a little bit more obvious to do them in one way or in another. So let's take a look at this line here, y equals x squared. This line here, that is y equals 1. This line that is y equals 4, which technically we don't need because the last line I'm going to draw is this one, where x equals 2. And we're looking at the region in here. It's almost triangular, but not quite. And we have two options. We can either start by looking at x values and then look at y values, or start by looking at y values and then look at x values. But if you think back to how I talked about setting up area, the thing to keep in mind is that the first coordinate is going to be given as functions, and the second coordinate is going to be given as constant values. In this particular example, I have y as a function of x right there in one of my bounds. The other bounds that I've written down are all constant values, but this one is variable. I have y as a function of x. There is nowhere that I have x as a function of y. Because of that, I'm going to talk about this region. The y values here are all less than or equal to x squared, and they're all greater than or equal to 1. Now, when you look going left and right at x values, sure, we're bounded by this curve still, but this right here takes care of the curve. So once I've established that curve, I want to look on the x-axis and say, where is the projection or the shadow of this region on the x-axis? And it's not given to us, but we know that this intersection point, the intersection between y equals x squared and y equals 1 happens when x is equal to 1. So we get that x is somewhere between 1 and 2. All right. So again, if you have one of your coordinates as a function of the other one, that's the one you want to handle first. Then, whatever coordinate you have left, look at the shadow of the region on that axis and figure out where that shadow ranges from, and that will give you the limits of integration there. So with that, we can set up our integral over this region of f of x and y dA is the integral. X goes from 1 to 2 of the integral y goes from 1 to x squared of xy dy dx. And from here, it works very much the same as it did before. Take care of the inner integral. The integral of xy dy, treat x as a constant, y as a variable. So it's going to be 1/2 of the coefficient x times y raised to 1 higher power, so y squared in this case, evaluated between y equals 1 and y equals x squared. It feels a little bit weird substituting in x squared for y in this expression, but that's exactly what we're going to do. 1/2 times x times x squared minus 1/2 times x times 1 squared. X squared is x to the 4th times another x is x to the 5th. Integral of x to the 5th is 1/6 x to the 6th. Multiply that by the 1/2 that's there. Integral of x is 1/2 x squared multiplied by the 1/2 that's there. Evaluate when x is 2, evaluate when x is 1. See, 2 to the 6th, 2, 4, 8, 16, 32, 64. 2 to the 4th is 4. And then we'll have 1 to the 6th, which is 1, minus a minus is plus. 1 squared is 1. And then just some fraction arithmetic. I could reduce 64 over 12, but it looks like I'm going to need a common denominator of 12 at the end anyway, so let's just do that. Uh, 64 minus 12 is 52, minus 1 is 51, plus 3 is 54. 54 over 12, well, they're both even, so it's going to be 27 over 6, and those are both divisible by 3, so we're going to end up with 9 over 2 as our final result. Yay, fractions. Let's take a look at one more example. I'm actually going to use the same function. F of x and y is equal to x times y. It's a fairly simple function to integrate. It makes me a little bit happy. And I'm going to set up my region here by sketching out the xy plane. And I'm going to draw two lines, y equals x and y equals 6 minus x. And I'm going to say that my region here is the space bounded between these two lines and the x-axis. That's my region R. You can certainly set this up the way we have before. I guess I should actually indicate that my goal here is to evaluate the integral over this region of f of x and y dA. All right, we have here that y is a function of x. And so it makes sense to try to start by looking at this region. The thing that is going to be a problem with doing that is because we have two different functions, we have two different bounding points. Right? That's annoying, but it's going to be doable. Figure out the intersection between these two lines. If I set x equals 6 minus x, that means that 2x is 6. That means that y is 3. And since one of the lines is y equals x, I know that that point is 3, 3. Likewise, I can figure out that we're looking at 0, 0, and 6, 0 as the other two endpoints. Right. So if I want to integrate with respect to y, then with respect to x, the same way we've set up before, I actually have to break this into two regions. I can take the integral, x goes from 0 to 3, the left side of this triangle, this space over here, where I'm bounded between the x-axis y equals 0 and the line y equals x. Then I can look at the other half, where x goes from 3 to 6, and y goes from 0 to 6 minus x, right, from the y-axis to this line of the same integrand, xy dy dx. That absolutely works. You have to go through and perform integration 4 times now instead of just twice, although the integrals, the first two integrals are going to look almost identical. The last two integrals will be a little bit more different. So I guess technically it's 3.5 integrations. But with the way I'm stating that, hopefully it's clear to you that we could do this a little bit differently. So let me redraw this region. And notice that if I integrate with respect to x first, the limit on the left and the limit on the right are consistent the whole way through this region. It means I have to do a little bit more algebra. Well, y equals x is the same thing as x equals y. That's almost no algebra whatsoever. Y equals 6 minus x, which means that y minus 6 is the opposite of x, which means that x itself is 6 minus y. It's a little bit more algebra. But I can set this up now. My shadow on the y-axis goes from 0 to 3. And on the x direction, on the left side, I have my line x equals y. On the right side, I have my line x equals 6 minus y. My function is still xy, but now I'm integrating with respect to x first, then with respect to y. For this particular example, I'm not going to claim that this direction is easier or harder. I think it's a little bit easier, but you have to think about the algebra. I'll show you another example in the very near future where that distinction is going to make a lot more of a difference. But let's go through this one just to make sure that we have it. take that inner integral first. Integral of xy dx is going to be 1/2 x squared y, evaluated between x equals y and x equals 6 minus y. And then we'll integrate with respect to y once we've simplified that mess. All right, so when x equals 6 minus y, we have 1/2 6 minus y squared times y. When x equals y, we have 1/2 y squared times y. All right, 6 minus y, the whole thing squared is going to be 36 minus 12y plus y squared. I guess I should slide this over so I have some more space to work. Um, half of 36 is 18. And then multiply by y, so it'll be 18y. Half of 12 is 6. Y times y is y squared. And then we'll have 1/2 y cubed. We'll have a minus 1/2 y cubed. Very conveniently, those things go away. Integral from 0 to 3 of 18y minus 6y squared dy. The algebra was a little bit messy, but not too bad to get here. Then performing this integration, fairly straightforward. Integral of y is 1/2 y squared multiplied by 18 gives me 9y squared. Integral of y cubed is, or y squared is 1/3 y cubed multiplied by 6, and that's going to be 2 y cubed. 3 squared is 9. 9 times 9 is 81. 3 cubed is 27. 2 times 27 is 54. 0 squared is 0. 0 cubed is 0. 81 minus 54 is 27. All right, there we have it. This time, let's look at a more complicated function. F of x and y is equal to x times e to the y cubed. And because the function is more complicated, let's look at a region of integration that's a little bit simpler. I'm going to set up a triangle here bounded by the y-axis, the line y equals x, and the line y equals 4. All right, so there's my region of integration. My natural inclination here, I have y written as a function of x, so let's set up y first. And if I'm looking at y, it's going from that line up. So it's y goes from x to 4. And then on the x-axis, remember that I collapse down and look at my shadow. Well, those two lines intersect at the point 4, 4, so I know that that's going to go x goes from 0 to 4 of my function, x e to the y cubed dy dx. But immediately we run into a problem. Integrals involving exponential functions are very straightforward. The integral of e to the u du is equal to e to the u. But in order for this to work, we need to have the same thing in both of these places. If I try a substitution and let u equal y cubed, I'll get that du is 3y squared times dy. And I don't have an extra y squared to use. Although I do have an x. And having an x might just be convenient. There's no guarantee that this will happen, but this is an elementary course, calculus level, not higher order applied math. So chances are we're not going to have to resort to looking things up at a table or going to numerical integration. We probably can do this by hand. Let me come down here and let me redraw the region on which I'm trying to integrate. And instead of calling that y equals x, I could write that same line as x equals y. And now, if I set up to integrate with respect to x first, I'm going to be looking at the integral x goes from 0 to y, and then I'll integrate y. Remember, after you've done this, you're looking at the shadow. So on the y-axis, my line goes from 0 to 4. Now I'm integrating with respect to x before I integrate with respect to y, and that makes all the difference. Because e to the y cubed, for the moment, is a constant. And so I'm integrating some constant times x, which is going to give me the same constant times x squared. Well, 1/2 x squared. When I substitute in x equals y, I get 1/2 y squared e to the y cubed. When I substitute in x equals 0, I get 0. And now, this is easy. Using that substitution, that we came up with before, if I let u equal y cubed, that means that 1/3 du is y squared dy, and I have y squared dy right here. I've always been a fan of changing my limits of integration when I do a u substitution. U of 0 is 0. U of 4 is 4 cubed, which is 64. And so my integral now is going to be the integral u goes from 0 to 64 of 1/6 e to the u du. And I know that that just gives me e to the u. So I get 1/6 e to the 64 power minus 1/6 e to the 0 power is 1. So just 1/6 e to the 64 minus 1/6. And that's it. All right. So you can think about regions of integration. Sometimes it makes sense to set up integrating with respect to y, then x. Sometimes it makes sense integrating with respect to x, then y. Sometimes it doesn't make a difference. Sometimes it makes all the difference in the world. A couple of things you have to think about as you look at these problems. So let me get my head back out of the way and let's look at one more for you to try. All right, so here is our region. I've got two curves here. A parabola on its side, x equals y squared minus 3, and a line, y equals x minus 3. I'll even save you some of the algebra. The points of interest here are -3, 0, 1, -2, and 6, 3. And I would like you to find the area integral on this region of our function f of x and y, again, 3x squared plus y squared dA. All right, take a few minutes, see what you can do with that. I'll see you in the next video.